In 1776, the founding fathers of the United States of America wrote the Declaration of Independence and also the Declaration of Momentum. And in that Declaration of Momentum, they defined linear momentum and impulse, as we will do. They looked at some graphs that related to impulse, and they talked about the laws of conservation of linear momentum, which we'll do right now as well. Linear momentum is one of those few terms that can be defined just by its equation. And so that definition is the same as the equation. So if you don't have this written down already, please do so. The equation, the symbol is usually a lowercase p, and then m times v. So what you want to think is that if something has high mass and high velocity, it's going to have a high momentum. Now the way we calculate this is pretty easy. As an example, let's say we've got one of these guys. Yeah, this is clearly, hopefully you are aware, if you have any culture at all, that this is a Goomba, and the stock Goomba mass, as everyone knows, is 60 kilograms. And let's say that he's moving at 5.0 meters per second. Pause it, calculate the momentum of this guy. Clearly, it's just going to be 60 kg times your velocity. Now the units, now this will turn out to be 300 kilogram meters per second. The end. There is no special unit for momentum. It literally is a kilogram meter per second. Something about Newton's second law that most people don't know is that it can also be expressed in terms of momentum. The IB sometimes asks you to show that you know this. Everyone who is anyone knows this version of the second law. But let's show how we can turn this into momentum. We can break acceleration down into delta v over delta t. Now, if you look at this term on top, mass times velocity, you know, is momentum. Mass times delta v is going to be change in momentum over delta t. So here is Newton's second law in terms of momentum. Now if you want to look at units, you can say that force times delta t is equal to momentum. And that gives us another set of units, because here we know that force would be in newtons, time is clearly going to be in seconds. So another unit for momentum is Newton seconds, which is the same thing as a kilogram meter per second. You also need to know and write down the definition of impulse, which is quite easy. It is simply the change in your momentum. You can also define it by its equation, which is just force multiplied by the time that you are applying that force. You can write it in a number of different ways. Change colors here. The symbol is usually just delta p. Maybe you can use an I, but you don't see it very often. And you can write it as m delta v, or you can also write it as f times delta t, or sometimes just f times t would be good enough. Now an example of a problem that you might have to solve. Let's say there's a guy and his bike and they weigh 70 kilograms, and they start out as going 12 meters per second. Then he puts on the brakes and he slows down to 6 meters per second over a time of, let's say, 4.0 seconds. And we want to know what is the average force that those brakes are applying as he does that. Pause it, see if you can solve it. Now what we can say is that impulse is going to equal f times the change in time. His momentum change is going to be the 70 kilogram mass times the 12 minus 6, or the minus 6 meter per second change in velocity because he slowed down. You call it plus or minus in this case. And that's going to be equal to his force, which we don't know, times the time of only 4 seconds. If you work this math out, you should get a force of about 105 newtons. Maybe we can round that to 2 sig figs, 110 or 100, whichever you prefer. When you look at a force versus time graph, some interesting impulse things can come to light. So as an example, one thing we like to do here at International School Vanilla is launch tennis balls into the air. And one thing we use is a 3-man slingshot where you get some rubber tubing and 2 people hold it on each side and a person in the middle will fire a tennis ball up in the air, which is awesome. Now you can also get a tennis ball just as high by just whacking it with a tennis racket. And let's say that the following is true, that both methods can get a tennis ball to the same height. And so they can both get it to the same initial velocity. So if the tennis ball starts at rest, we can say that they deliver the same impulse. So now let's say that we're going to look at a graph of the impulse, or the force versus time, from the slingshot. And let's say that it starts relatively weak, and then it builds, and then it drops off quite steeply, that force, as the ball flies off the slingshot. So that's going to be for the slingshot. Now let's say with a different color, we have the tennis racket. That's a much shorter impact time of the ball on the strings. So let's say that it just flies up like that. And you have a sharper or narrower time increment, but it can deliver a higher force in that amount of time. So this is for the racket, right there. Now what we can say is that the areas that are underneath here are going to tell us the impulse on the ball. You might have to use some calculus to exactly calculate this. If you had to do this in an IB situation, they would give you nice shapes like a triangle or a rectangle to calculate that area. But what we can say is, if this is true, the same impulse, we can say then that these must have the same areas. Linear momentum, in some cases, can be said to be conserved if the following is true. Now write this down. If you don't have it written down already, memorize it. If you do have it written down already. Now, let's say, as an example of when it would be concerned, if you have no external forces. Things like friction are often external forces and blow this out of the water. But let's say that we've got a jack-o'-lantern that, let's say, is floating in space, which would be pretty awesome, and it has a stick of dynamite or a large firework in it, which would also be pretty awesome. And it's just floating here, not moving, so we could say that its momentum is clearly 0. It's not moving. And then it explodes. That is an internal force, so the net momentum has to still be 0 because it's an internal force, not an external one. And that is because if you add up all the momentums of these pieces, and momentum is a vector, that's also key. Momentum is a vector. All of these vectors would have to cancel out to still give us this momentum of 0 because momentum would be conserved in this situation. More examples of this coming your way soon.